Today's topic, carbocation stability. This lesson requires familiarity with resonance, primary, secondary, tertiary nomenclature, and hybridization. A carbocation refers to a carbon with 3 bonds and 1 positive charge. Therefore, a carbocation is an electrophile. Carbocations are an important class of intermediates as they are formed in many organic reactions such as SN1, E1, electrophilic aromatic substitution, and etc. A positive carbon is generally not happy. Thus, carbocations need to be stable to be formed. The more stable a carbocation is, the faster the reaction proceeds. So, what makes a carbocation stable? The first contributing factor to carbocation stability is the presence of adjacent carbons. The more carbons are present adjacent to the carbocation, the more stable it is. Thus, a tertiary carbocation is more stable than a secondary one, and a secondary carbocation is more stable than a primary one. But why is that? Carbocations are planar molecules and sp2 hybridized. This means that they have an empty p orbital. The empty p orbital is stabilized through hybrid conjugation, which is the weak donation of sigma bond electrons into the empty p orbitals. The sigma bond must be parallel to one lobe of the empty p orbital. Thus, the more alkyl groups there are on the carbocation, the more possibilities there are for hyperconjugation, and the more stable the carbocation is. Depending on the textbook you use, you might also read that the alkyl groups shift the electron density toward the positive charge as they are electron donating. This is called inductive effect. Thus, the more alkyl groups there are, the more electron density is shifted toward the positive charge, and that is why the more substituted carbocations are more stable. The second contributing factor to carbocation stability is resonance, which could arise either from a double bond or lone pairs of electrons. So in the following example, the carbocations with the double bonds are more stable than the ones without the double bonds. The first one is called an allylic carbocation, and the second one is called a benzylic carbocation. The reason for this stability is because the positive charge is shared between multiple atoms because of the overlap between the empty p orbital of the carbocation and the p orbital of the pi bond through resonance. As a refresher, the movement or sharing of the electrons between multiple atoms is called delocalization. So as we can see here, there are two resonance structures for these types of carbocations, which stabilize the carbocation. The carbocations on the right, on the other hand, do not have any resonance structures. Another possibility for resonance arises when the carbocation is adjacent to an atom with lone pairs of electrons. For example, in the following examples, the alcohol and the amine carbocations are more stable. This is because the nitrogen or oxygen can donate their electrons to form a new pi bond through resonance, and thus stabilizing the carbocation. On the other hand, no resonance structures are possible for the carbocations on the right-hand side. The general trend of carbocation stability is shown here. A primary allylic and a primary benzylic carbocation generally have the same stability as a secondary carbocation. However, a secondary allylic carbocation is more stable than a secondary aliphatic carbocation because it is secondary and also allylic. Let's do some practice now. Pick the carbocation that is more stable and explain your answer. You could pause the video to see how many you can get right. Let's look at the first example. The one on left is a secondary carbocation, whereas the one on right is a primary carbocation. Remember, the more alkyl groups there are around the carbocation, the more stable it is. So the secondary carbocation is more stable. Moving on to the second example, the one on left is a tertiary but also an allylic carbocation. The one on right is only a tertiary carbocation. So the one on left is more stable because it is stabilized through resonance as well. Lastly, both of these carbocations are primary. However, the one on left has a CF3 group. Fluorine is electron withdrawing, so it makes the positive charge even more positive by pulling the electrons towards itself and destabilizing the positive charge. Thus, the primary carbocation on left is more stable. So in conclusion, carbocations are more stable if there are more alkyl groups around them. They are also more stable if there is a possibility of resonance through either a double bond or lone pairs of electrons. Hope you guys found this useful.